In this video, we're going to talk about topic 3.1, which is the chain rule. Our essential question is, how do you use the chain rule? And our I can statements, which we will use for the entire lesson, which is actually a very big lesson, is I can use the chain rule to take the derivative. I can combine different rules together to take the derivative, and I can take a derivative with repeated use of the chain rule. So to begin here in the left-hand column, if you ever have parentheses invisible or not, you must use the chain rule. So that's a good indicator that that we need the chain rule. And remember, sometimes we write things without parentheses in it, such as natural log of x, e to the x, sine of x. Sometimes we don't, mathematicians are lazy and we don't write parentheses when we really should. These things should have parentheses around them. We know we need the chain rule when we see something like that. So the most powerful and important rule in differentiating is the chain rule. So far we have learned several derivative formulas and rules. However, all of our problems only contained a singular x as the argument. Consider the following functions and see how they might look with and without a chain rule. So if we have the function f of x equals x squared plus 1, that has a singular x. I could change that function to f of x equals something squared plus 1, and I put in a cosine x in there. And it's the same problem, but you notice instead of the x squared, I now have another function inside of it, cosine x. Then we have f of x equals sine, and instead of writing the x, I'm going to write e to the x. Notice I have another function on the inside of the function. Let's look at the next one. So f of x equals e. Instead of writing x, I'm going to write x squared plus 1. And then instead of writing just the natural log, I am going to write sine x. So do you see how the inside function is different than the outside function? Remember, in the past, we've had f of g of x, function composition, where the g of x is the inside function. So that's what's getting at. We need to know what the inside is, and we need to know what the outside is. One last example of this, we've got f of x equals, instead of just square root of x, maybe square root of 1 plus x squared. So in order to tackle these new functions, we're going to revisit the meaning of the derivative. So when we're going to consider dy dx, and we want to know, what does dy dx means? So dy dx means the derivative of our function y with respect to x. What if instead, though, I turned it to dx dt or du dy? So dx dt means the derivative of x with respect to t. So the x is acting kind of like the y did, and the t is acting like the x did. And then finally, du dy means the derivative of u with respect to y. All right, so we're going to let y equal 2t cubed plus 4, and we're going to find dy dt. All right, so dy dt. So this is just reviewing kind of some of our rules from before. So this cubed would go in front, right, and multiply it by the 2. So we'd have 2 times 3t, and I'm subtracting 1 squared. And the derivative of 4 is 0, so I'd really end up with 6t squared. Now I'm going to find the derivative of both of these things. So the derivative of y with respect to x would be, I'm going to bring the 4 in front. So I've already got a 3 hanging out there. So 4x subtracting 1 cubed. And the derivative of 2x is 2. So we would really write this as 12x cubed minus 2. And the derivative of x with respect to t would just be 2t.